A modern distributed architecture processes millions of incoming requests every single second, routing them efficiently across thousands of individual interconnected microservices. Applying a consistent security model across every single node without throttling traffic requires a specific architectural approach. We achieve this by splitting the security model into two separate domains, determining who is making the call and determining what that caller is allowed to execute. Authentication answers the first question. It is the strict process of verifying an identity before any business logic runs. The side-by-side logical tree shows the division. Authorization validates permitted actions. But mixing verification and access control in one microservice creates security vulnerabilities. Therefore, the platform removes authentication from the service level, handling identity verification entirely upstream. With identity handled upstream, the developer's sole responsibility is modeling the authorization rules that govern their specific endpoints. This modeling requires configuring three core layers: permissions, audiences, and ownership. Secure API development relies on defining these explicit policies, rather than writing imperative infrastructure to check passwords and tokens. Instead of each service acting as its own gatekeeper, all incoming traffic routes through a central platform gateway. It absorbs the raw request, executes authentication flows, and strips away external session cookies, tokens, and keys. Before routing the request down to the target microservice, the platform injects a standardized, structured identity context object into the payload. This context contains explicit identifiers, sending exact account IDs, meta-site IDs, and visitor IDs directly to the service. Developers must treat this identity context as mathematically trusted input. The identity has already been verified by the platform. Because the platform guarantees this context, services must never parse authorization headers or validate session cookies internally. Building custom authentication middleware inside a microservice is strictly prohibited. It introduces redundancy and breaks the centralized trust model. The platform defines the identity type in that context. Calls originate from logged-in Wix users, anonymous visitors, or internal backend services. Each identity type maps to a distinct usage pattern. An external third-party application requires different security evaluation than a back-office administrator. Consuming standardized identity context shifts credential management liability off the developer's plate, eliminating a major source of technical debt across the organization. Once a service receives that trusted identity context, it evaluates the request against its defined rules. The foundation of those rules is the permission. It is the atomic unit of access control, operating strictly at the endpoint level. In remote procedure call design, every single method must map to exactly one unique permission. As this schematic shows, these permissions are declared statically within the proto-schema. When the schema is merged, the platform compiler automatically generates the enforcement mechanisms. To manage access at scale, these generated permissions are organized into scopes. Default scopes assign read, write, and delete privileges, allowing developers to map specialized endpoint operations to broad user roles. Generating permissions directly from the schema removes the variance of human implementation across different teams. Treating the protofile as the strict single source of truth guarantees uniform access control across the entire ecosystem. A cryptographically valid permission is not enough to secure an endpoint. An internal service might hold a valid write permission, but it should not be allowed to update a consumer's billing profile. This logic gate illustrates the solution. Developers define an audience guardrail that restricts which identity types can execute the method. A public app routes successfully, while a back-office admin is blocked. Audience restrictions sit at the top of the evaluation hierarchy. If the identity type does not match, the request is terminated immediately, even with valid permissions. Permissions dictate the allowed action. The audience dictates the allowed actor. A secure API requires both. Even with correct permissions and a valid audience, multi-tenant environments face one final vulnerability: separating users who possess the exact same permissions and audience classification. Consider two identical identity avatars, both site members attempting to read an order profile. The first requests an order associated with its own account and connects. The second attempts to read that exact same record and is blocked. This is enforced by ownership rules. The system compares the specific account identifier provided in the trusted identity context against the target data's attributes. Authorization constraints run these checks deep inside the data operations themselves, ensuring safe writes and preventing unauthorized modifications during bulk updates. By strictly matching identity context to data attributes, ownership rules guarantee absolute isolation between users and prevent lateral data leakage. At runtime, all of these complex design time policy configurations must systematically execute in a rigid, highly specific sequential order. This horizontal pipeline visualizes the process. Every API call must successfully navigate a 6-step authorization sequence. Step 1. The request arrives from an external or internal source at the platform gateway. Step 2. The platform validates the identity and propagates the trusted identity context down to the service. Step 3. The system checks the required permission defined in the proto-schema against the requested operation. Step 4. The audience constraint verifies that the specific identity type is permitted to call this endpoint. Step 5. Ownership logic evaluates the data layer to verify the caller actually owns the specific resource requested. Step 6. Only after all 5 preliminary checks pass does the system execute the actual business logic. In the Nile architecture, the platform enforces this entire multi-layered sequence automatically. Mastering this layered authorization matrix ensures API security scales gracefully as systems evolve, preventing the catastrophic technical debt caused by manual policy enforcement.